Hello, sir. Can we start? Okay. So, good evening, everyone. This is Sushma. So today we'll be seeing the semester 2 assignment questions. Okay. So we'll see the first question. Obtain the directional derivative for a scalar field I of x y z is equal to 5xy minus 3y square z cube at the point 0, 1, minus 1. So in the direction of I plus j cap plus k cap. Okay, so this is the question that is given to us, right? Yes. So we'll see the solution for it. So now, if we need to find the directional derivative of a scalar, so we will use the gradient operator. Okay, so this is the representation for a gradient operator. Okay, so what is the formula for the gradient operator? That is I into dou divided by dou x plus j into dou divided by dou y, k into dou divided by dou x, dou z. Okay, so this is the formula that is given for the gradient operator. Okay, so what is I, j and k cap here? They are the unit vectors, okay, along the direction x, y and z. Okay, so what is this dou by dou x? So they are the partial derivative operators. Okay, so they are nothing but partial derivative operators. Okay, with respect to x, y and z. Okay, so I, j and k cap will be the unit vector along the x, y, z. So now the directional derivative of the scalar field, that is phi, in the direction of a unit vector u cap. Okay, so what is the formula? D underscore u phi, that is equal to gradient operator into phi into u cap. Okay, this is the formula. Okay, so dot will here denote the dot product. Okay, so in this case, the scalar field is nothing but phi into x comma y comma z, that is 5xy minus 3y square z cube. Okay, so now we need to find the directional derivative at this given point. Okay, in the direction of I plus j plus k cap, that is nothing but a unit vector. So first we will calculate the gradient, okay, at this given point, which is given in the question. Okay, so this is gradient phi is equal to, we will just substitute the values that is given in the question, that is in the form of equation. Okay, so now at this point we will have to just substitute the values of x, y and z. Okay, so therefore we will be getting it as minus 9. Okay, so the directional derivative of the scalar field at the given point that is given in the question, which is 0, 1 and minus 1, is equal to minus 9. Okay, so this would be a final answer. Next, so this next question. So calculate the work done by a force F vector, which is equal to 4 y cube z cube I cap minus 2x square yz cube j cap plus 3xy square z cube k cap. Okay, in moving a particle along the path which they have given 3 equations between the points t is equal to 0 and t is equal to 1. So this is the time given to us, and they have given 3 equations and the F vector. Okay, so now we need to calculate the work done by that force. Okay, so in order to calculate the work done by the force, which is F vector, okay, in moving a particle along its path, so first we will use the line integral of the force of along that path. Okay, so the line integral is the formula which is given by W is equal to integration of AB F vector into R of T dt. Okay, so what is A and B here? They are the initial and final values of the parameter T. Okay, and what is R of T here? It is the equation, that is the position vector. Okay, so this would be given in the question. These values would be given in the question of the particle as a function of t. And what is r of t? That is dx by dt I cap, dy by dt j cap, and dz by dt k cap. What are all those? Those are the velocity vector of particle as a function of t. Okay. So in this case, where they have given x is equal to t, y is equal to t, and z is equal to t. So we will have these equations that is given in the question. These equations are given in the question, right? Yes, and t is equal to 0 to 1. That is also given in the question. So therefore, we will find the position vector of the particle. That is r of t is equal to ti cap plus tj cap plus tk cap, right? And this is the formula for the velocity vector. Okay. Yes. So now we will just substitute the values that we have in the question. Okay. So therefore we will get W is equal to 1. Okay. So therefore this is the work done by the force F cap. Okay. Which is moving the particle from this 0, 0, 0 to 1, 1, 1. Okay. Which is equal to 1. Since we have got W is equal to 1. So the work done by the force F vector is equal to 1. So this would be our final answer. Okay. Yes. Moving on to the next question. So using the divergence theorem, evaluate integration of A vector dot n cap ds, where this A vector equation is given over the surface of a sphere with its center at the origin and a radius of 8 units. Okay. This is the question. So the divergence theorem, which is also known as the Gauss theorem. Okay, this is a very important point we need to understand. The divergence theorem is also known as the Gauss theorem. So what does it state? It states that the surface integral of the dot product of a vector, which is vector field, which is F vector, over a closed surface, which is S, is equal to volume integral of the divergence of F vector. Okay, over the volume enclosed by S. Okay, so how would you write this theorem in the form of mathematically? So there is the formula that we have. Okay, integration of S vector into n cap ds is equal to integration of V into gradient dot F vector into dv. Okay, so what is S vector here? It is the surface area vector. Okay, what is n cap? It is the unit vector, so the surface. And what is gradient into F vector, which is a divergence of F vector. Okay, yes. So in this case, we have a vector field. Okay, this equation which was given in the question. Okay, which was given to us in the question. And now we will evaluate the surface integral. Okay, so what is the formula for that? Integration of S vector dot n cap ds. Okay, so this is the surface of over the surface of this sphere with radius as 8 units. Okay, so now when we use the spherical coordinates, okay, in order to parameterize the surface area vector is given by this formula. Okay, so this S vector will represent the surface area vector. Okay, and the unit normal vector. That is the unit normal vector. Okay, where r is the radius of the sphere. Okay, and what is theta? It is called as the polar angle. What is phi? It is azimuthal angle. And r cap is nothing but the unit vector. Okay, so now we will have the formula for the surface integral. Okay, so there is the formula for the surface integral. Okay, so now we need to calculate the divergence of the vector field A cap, A vector, right? So we will compute this A vector. Okay, so we will use this formula. Okay, so just substitute the values that is given to us. Okay, so then we will substitute this into the divergence theorem. Okay, so this is what we get when we substitute it in divergence theorem, right? Yes, so now we will use the spherical coordinates in order to find the volume integral. Okay, so we will just substitute these spherical coordinates value, okay, into the volume integral formula. Okay, then we will get it as 64 pi by 3. Okay, so what would be the surface integral over the sphere? That is given by this formula. Okay, so S vector represents the surface integral, which is n cap into ds, that is 64 pi by 3. So this is the surface integral of the sphere. Okay, yes. So next, moving on to the next question. Explain with the help of diagrams what spherically and cylindrically symmetric charge distributions are. What is the electric field at a point inside a hollow metallic sphere of radius r? Okay, so here we will explain with the help of diagrams what are the symmetric charge distribution. Okay, and what is electric field, okay, inside the hollow metallic sphere of radius which is having as r. Okay, a r having volume charge density this. Okay, we will see the solution for this. So a spherically symmetric charge distribution, okay, is a distribution of electric charge where the charge density is same at any point on the sphere, okay, and which will be centered at the origin. So if we take a cylindrically symmetric charge distribution, on the other hand, so it will be the distribution of electric charge where the charge density is same at any point on the cylinder centered at the origin. Okay, so here at any point it will be equal. So in case of spherically symmetric charge distribution, but in case of cylindrically symmetric charge distribution, okay, so it is a distribution of electric charge, okay, where it will be same at any point on the cylinder. Okay, so here it is a sphere, so here it would be a cylinder. That is the difference. Okay, so now we will see those two diagrams. So this is the diagram that we are seeing. Okay, so now when we come to the electric field at any point inside a hollow metallic sphere, okay, which is of radius r, okay, which has volume charge density, okay, the electric field inside a hollow sphere would always be equal to 0. Okay, when we come to the electric field at a point inside the sphere, okay, the electric field would be equal to 0. Okay, this is because of the Gauss law. Okay, so we have seen the Gauss theorem. Okay, so this Gauss law states that the electric field at any point inside the hollow sphere would always be equal to 0. Okay, so when it is 0, only if it has a uniform charge density. Okay, so this is because the electric field due to infinite charge element, okay, at any point inside the sphere will cancel out the electric field due to its opposite element. So when it has an opposite element, it will always cancel out the electric field. Okay, that is what this point means. Okay, if the hollow sphere has a uniform volume charge density, then the electric field would be 0 in case of a sphere. Okay, so next question. Two particles carrying 4C and minus 2C charges, okay, they are carrying these two charges, are placed on a 1 meter long straight wire. Okay, so determine the point on the line joining these particles where the electric potential is 0. Okay, we'll see the solution for this. So now when we have to find the line that joins the two particles, okay, where there is an electric potential which is equal to 0, okay, so we need to find the position where that electric potential will be cancelled. Okay, so we will consider, let the distance of the point from 4C charge be equal to x. So this we will consider. Okay, then the distance from the minus 2C charge would be equal to 1 minus x. Okay, so these are the two values that we are considering. Okay, as the wire is how much long? It is 1 meter long. Okay, now we have the electric potential at this point due to the plus 4C charge will be equal to this. Okay, V1 is equal to KQ1 divided by X. So now the electric potential at the point due to minus 2C charge would be this. Okay, that is minus KQ2 into, so here it is not X, it is 1 minus X we have considered for minus 2C charge. Okay, so the negative sign in front of K into Q2 indicates that the potential is negative because it has a negative charge. So now we will set V1 will be equal to V2. Okay, so so that we will have these both equations to be equal. So k into q1 divided by x is equal to minus k into q2 divided by 1 minus x. Okay, so we will just simplify this equation. So what we will get, that is 4 divided by x is equal to 2 divided by 1 minus x. So when we solve for x, we will get the value of x as 2 by 3. Okay, so therefore, what is the electric potential when it is 0 is at a distance of 2 by 3 meter, since x is equal to 2 by 3 from these two charges. Okay, so from plus 4c charge and 1 by 3 meter from minus 2c charge. Okay, so therefore, this is the final answer that we are getting. Okay, next question. So explain the phenomenon of polarization of a dielectric. Show that when a dielectric material is filled between the plates of a capacitor, the value of capacitance will increase by a factor of k. Okay, the dielectric constant of the material. Okay, so we'll see the solution. So the polarization of a dielectric material, okay, will refer to the process of aligning its electric dipoles. Okay, so when do you align? It is in the presence of a electric field. Okay, so when a dielectric material is placed in an electric field, the positive charges, okay, in the atoms, or it can be a molecule, okay, will be attracted towards the negative plate. Okay, so always the positive charge will always attract towards the negative plate of the capacitor, while the negative charges will always attract to the positive plate. So it is vice versa. Okay, so this will result in the separation of charges. Okay, so when the positive charges will always attract towards negative plate and negative charges will always attract to the positive plate. So in this way, the charges are getting separated, okay, within the dielectric material, and hence it will create the electric dipoles. Okay, when there is a separation of charges, it is going to create the electric dipoles. Okay, so what is the direction of that electric dipoles? Okay, the direction of the electric dipoles in the dielectric material is aligned with the direction of electric field. Okay, so always the direction of electric dipoles will be aligned with the direction of the electric field. Okay, so this alignment of the dipoles. So when the dipoles are aligned in this way, it will create an extra additional electric field within the dielectric. Okay, so that would always be opposite in direction, which is always opposite in direction to the external electric field. Okay, so now this opposite electric field will weaken the electric field within the dielectric. Okay, so there is an electric field which is opposing, so this will always weaken the electric field which is within the dielectric. Okay, so what happens when it is weakening the electric field within the dielectric? It will reduce the potential difference. Okay, it will reduce the potential difference which is across the capacitor. Okay, so now the charge on the plates will remain the same. Okay, so there is no change in the charge on the plates. It will remain the same, which results in increase in the electric flux density. Okay, so this will be increased, okay, within the dielectric. Okay, so now we will consider a parallel plate capacitor. Okay, so they have given plates of area A and separation distance D, okay, which has a thickness of T and a dielectric constant K. Okay, so there is a parallel plate capacitor where they have given the area as A, okay, separation distance as D, and filled with the dielectric material of thickness T, and the dielectric constant as K. Okay, so now we need to have the formula for capacitance of this parallel capacitor. Okay, so this is the formula that we are seeing for the capacitance of this parallel plate capacitor, where the symbol will represent the permittivity of a free space. Okay, so now when we have a dielectric material which is filled between the plates of the capacitor, there is an electric flux density that would be given, okay, within the dielectric, which is related to electric field E, okay, which is given by this equation. Okay, so this is an equation which will denote the dielectric material when the plates are filled. Okay, when the material is filled between the plates, so the electric flux density will be represented by this formula. Okay, so now we know the symbol will represent the permittivity of the dielectric material. Okay, so now when there is no dielectric material, okay, so what would be the formula? Okay, so this formula would represent the electric field between the plates when there is no dielectric material. Okay, so what is V here? It is the potential difference across the capacitor. Okay, so now when there is dielectric material which is filled between the plates, the electric field is reduced by a factor of K. Okay, the electric field will be reduced here, which is of factor K. Okay, and the dielectric constant of the material. Yes, so the electric field within the dielectric will be given by this formula. Okay, which is E is equal to E dash is equal to E by K. That will be equal to V divided by D divided by K is equal to V divided by K into D. Okay, this is the formula for the electric field within the dielectric. Okay, so now we will have the formula for the electric flux density, which is within the dielectric. Okay, so that is D dash is equal to E dash is equal to V divided by K D. Okay, so the electric field which is due to the free charges will be given by this formula. So this formula E free will represent that electric field due to the free charges. Okay, so now we have to calculate the total electric field. Okay, so what is the formula for total electric field? This is the formula. Okay, E total is equal to E free plus E dash. So this is the very important formula we need to remember. So E total is equal to, we just need to substitute the values that we have given in the question. Okay, so what is the electric flux density within the capacitor? So this we need to just substitute whatever we have got in the E total. Okay, so the electric charge on the plates would be given by this formula. Okay, so it is Q divided by Q is equal to D total, okay, into A, okay, which is equal to 2 into A V divided by K into D. Okay, so now what we have to calculate? Next, we need to calculate the capacitance of the capacitor. Okay, so with the dielectric material, so that is given by this formula. Okay, so what is the capacitance of the capacitor with a dielectric material, which is K times greater than the capacitance of the same capacitor? Okay, so whatever we have the capacitance of the capacitor with the dielectric material, okay, which is K times greater than the capacitance where there is no dielectric material. Okay, yes. So next we have the next question. Okay, so this question we will mostly be probably seeing in the next class. Okay, and guys, you can take this question as a homework question. Okay, so we will solve this question. Okay, and we will be back to the next class, where again in the next class I'll be teaching you this stuff. Okay, yes, so see you guys in the next class. Until then, take care. Bye bye.